Hello, hello! In this video, we're going to take a look at the recursive algorithm for division, which takes into n-bit integers x and y, where y is greater than or equal to 1, and then it's going to return the quotient and remainder of x divided by y. Now, before we get started, we should be really careful about what that means. What this really returns is, so we'll have an input, which is my integers x and y, and my output is going to be integers a and b such that x equals a times, well, actually, let's call these q and r. That'll be a little nicer. Q and r for quotient and remainder. So there we go. So x is going to equal my quotient times y plus my remainder. So that's what it really means. This ST, that just stands for such that. Which is a little different because it's not just a number that it outputs. It outputs two numbers, and they're numbers that satisfy a specific equation. So we're going to want to prove that this algorithm works. We're going to do that using induction, and the fact that basically what we have is this equation that is satisfied is going to make that induction argument a little bit harder, but not too bad. So before we even do that, let's go ahead and see what it's going to do. So first of all, if x is 0, it's going to return qr 0, 0. It's going to say that my quotient 0, my remainder 0. And we can briefly check that that should work. If x equals 0 and then we set q and r equal to 0, everything's fine. We should say one other thing about this equation. Because it's not just q and r satisfying that. We also need that 0 is less than or equal to r is less than or equal to y minus 1. That's also going to be important here. Okay, so, and that is also true here. So whatever y is, if in this base case, if r is 0, 0 is clearly between 0 and whatever y minus 1 is, because y can only be ever as small as 1. So 0, 0 definitely works if x equals 0. And we'll state that a little bit more formally later. Now, if it's not 0, we'll go on to the rest of this program. And what we're going to do is I'm going to start with some values q and r, which will be the quotient of x divided by 2, rounded down, comma y. And then we're going to take those q and r values, we're going to double them both. If x is odd, we're going to add 1 to r. And then if r is too big, if r is bigger than y, or greater than or equal to y, then we're going to subtract y from r and then add 1 to q. And then obviously this gives us the right answer, right? Well, that's why we're going to prove that it's true. So let's go ahead and prove that this works. And one last thing before we do that. Note that this right here is a recursive call of the algorithm. So we're dividing x over 2y. That's recursive. We're going to recursively call smaller and smaller things until we get down to the base case. And the idea is, if we can inductively prove this, basically we say, hey, sure, this divide step works right by induction. So we should be able to conclude that the overall algorithm works right. So let's go ahead and prove by strong induction. And if you're not used to strong induction, it's very similar to normal induction, and I'll state the difference when we get there. So to start any inductive proof, we need to think about our base case. And our base case is also the base case of our recursive algorithm. It's going to be when x equals 0, we return q equals 0, r equals 0. Note that let's now plug these things in. 0, when x equals 0, equals q, that's going to be 0, times y plus r, that's also 0, and 0 is less than or equal to r is 0, it's less than or equal to y minus 1, and that's true because y has to be at least 1. So we satisfied both of our conditions there. This returns correctly in the base case. Now we'll do our induction step. And what we're going to assume divide returns correctly for all 0, I'll say 0 is less than or equal to x prime is less than the x we're looking at. So what do we return? What do we do? First, we obtain, let's take a look at what this divide step does. And actually, we're going to need to split this into two cases. So let's go ahead and do that. So our first case is going to be what happens when x is even. First, we find, we evaluate, I guess we should say. We run, we find, we evaluate. I'm going to call these q prime and r prime just to show that they're not going to be our final q and r. And these q prime and r prime are going to equal divide of x over 2, comma y. So, since this is correct, by induction, we assume this is correct. We assume this runs correctly. So, and I'm going to take a little step here. What that's going to tell us is that x over 2 equals, and I'm not going to write the floor sign. The reason I'm not is because since x is even, the floor of x over 2 is just x divided by 2. There's no rounding needed there. So x over 2 equals q prime y plus r prime. And it also tells us that 0 is less than or equal to r prime is less than or equal to y. Okay, so that's a good start for us, but what does that tell us about x? By multiplying both sides of this by 2, by multiplying x over 2 equals q prime y plus r prime by 2, we get x equals 2q prime y plus 2r prime. And I'm going to add some parentheses there, and we're going to note, thus, if 2r prime is small enough, basically if this is less than or equal to, I should have said y minus 1 back there, my apologies. If 2r prime is less than or equal to y minus 1, we're done. Because the algorithm returns 2q prime and 2r prime. And let's just kind of go back and make sure we know why that's true. Because basically, what does that mean? So we found this q prime, this r prime. Then we found q by doubling those. Basically, we doubled each value. It's not odd, so we ignore that. We're assuming that r is fine, that it's not greater than or equal to y. And by r, in this case, we mean 2 times r prime. So it then just returns 2q prime and 2r prime. Okay. But if 2r prime is greater than or equal to y, we're going to note that x equals 2q prime y plus 2r prime. This is also equal to 2q prime minus y, or minus 1, y plus 2r prime. Actually, I think that's a plus 1. It is a plus 1. 2q prime plus 1, y plus 2r prime minus y. Okay. And you can convince yourself that's true. We distribute the y, and that will get us 2q prime y plus y. And then that plus y cancels out the minus y over here. So we see that these also satisfy this equation, x equals 2q prime plus 1 times y plus 2r prime minus y. So those also should work as our quotient remainder as long as this remainder is small enough. So clearly, since 2r prime is greater than or equal to y, that shows us that 2r prime minus y is greater than or equal to 0. Also, since y prime, or since r prime is less than or equal to y minus 1, that means that 2r prime minus y is less than or equal to 2y minus 1 minus y, which equals 2y minus 2 minus y, which equals y minus 2. So we have that not only does x equal 2q prime y plus, sorry, not that, wrong thing. Since not only does 2q prime plus 1 y plus 2r prime minus y, not only is that true, and also we have that 0 is less than or equal to 2r prime minus y, which is less than or equal to y minus 1. And we can see that because clearly y minus 2 is less than or equal to y minus 1. So we should return 2q prime plus 1 and 2r prime minus y, which is correct. Let's go back to the algorithm, see that that's what it does. Yes, so when this is odd, or when this is even, we double q prime, we double r prime, and then we don't do this because it's not odd. And then if r is greater than or equal to y, we subtract y, so that brings us to 2r prime minus y. And then for q, we add 1, so that brings us up to 2q prime plus 1, and we return that, which is what we have here. Okay. And we've shown that in both cases, this works. So in the main case where x is even, we saw that if we basically do this division thing, If 2r prime is already small enough, if it's already less than y minus 1, then we get the right answer. If it's too big, then we make this modification, and what we get is the right answer. So in all cases where x is even, we're done. Now we need to do the case where x is odd. And I think we're going to do that in another video. So that's enough for now, but have no fear. It's very similar to what we just did. It's just instead of an x over 2 here, we're going to have an x minus 1 over 2. And this inequality is going to be a little bit more tight. So we'll go ahead and do that in the next video.